This is a lecture for Wednesday, 11/22/2017, and also for the people on the Thursday class, which is Thanksgiving. I'm going to cover the remaining of the chapter, what I feel like would be a good lecture's worth of material. So if you can't follow along or you have trouble with it, just feel free to text me or email me, and you have the numbers. So let's go ahead and continue. We were talking about substitution reactions. So this slide really could be substitution reactions in general. And one of the things about substitution reactions is that you can create a wide variety of different compounds. So if you use hydroxide as a nucleophile, then you can end up with an alcohol. If you use tertiary amine, you can end up with a quaternary ammonium ion, which is usually known as a quaternary ammonium salt. And if you use other functional groups, you get direct replacement to form, for example, alkynes if used in acetylide ion. And one of the features about these reactions is they're not reversible. That is, they can't revert back to the reactants because the weak base, which is the leaving group, can't replace the nucleophile, which is a strong base, simply because of bond strength differences. So there's another way to synthesize amines, and that's through the use of methyl iodide. Methyl iodide is a common methylating agent. It is very susceptible to nucleophilic substitution. Because it's a methyl group, this reaction mechanism is going to be an SN2 reaction mechanism. And you end up getting a substituted amine. And you have the iodine as the leaving group. Now, you'll notice that this group is protonated, and as a result, they use a base like potassium carbonate. Sometimes they'll use solvents that have basic properties like pyridine to remove the excess hydrogen. Once you remove the excess hydrogen, this pair of electrons, that is, once you remove the hydrogen on that functional group, the amine, you can add another methyl group through an SN2 reaction, and again, the sodium carbonate can be used to remove that excess proton, that is this proton that's here, and once that proton's gone, you can subsequently add another group through the use of another equivalent of methyl iodide, and as a result you end up with a quaternary ammonium salt. If you use methyl iodide, it's a quaternary ammonium iodide. So the potassium carbonate's purpose is primarily just to keep it in its basic form so that it can act as a nucleophile. Otherwise, amines are a little bit different than a lot of the other nucleophiles in that when it gets protonated, it is no longer active. But if you can activate it by simply exposing the proton for subsequent addition reactions, like these guys. So to summarize, you have an overall rate of reaction that is comprised of two rates from two different mechanisms. You have the SN2 reaction mechanism and you have the SN1 reaction mechanism. Both of them depend on the concentration of the alkyl halide, but the rate at primary alkyl halides and methyl halides is fastest for SN2 reactions because you can't form carbocations on primary or methyl alkyl halides. The other simplifying thing is to look at tertiary alkyl halides, and in tertiary alkyl halides, they're too sterically hindered, so you can't have a backside attack. Also, carbocation stability is much better at tertiary alkyl halides, so when you have a stabilized alkyl halide, so this could also mean like secondary alkyl halides, which are resonance stabilized, you can have SN1 reactions. Now, one of the things your book does, and it helps to simplify this whole section, is if you think about secondary alkyl halides, that you only have SN2 reactions if the carbocation formation is slow, to make up for the large concentration of the nucleophile in a solvolysis reaction. So really, the important aspect of this is that it's a solvolysis reaction. If you have a solvolysis reaction, the nucleophile is your solvent, and because you can increase this concentration, that increases the overall rate contribution of the SN2 reaction to a point where SN1 reactions don't matter. Like I talked about in class though, if it's not an SN2 solvolysis reaction, then what you have to consider is you have to consider solvent, and the other aspect you have to consider is nucleophilicity. That is, how good the nucleophile is. So if you have a good nucleophile, that is something with a negative charge and a lone pair, that's primarily SN2 favoring. If you have a bad nucleophile, say something like H2O, if you have H2O, then what happens is the reaction's too slow for the nucleophile to come in, and so the carbocation will form. So we started this chapter talking about the two possible mechanisms when you have this Y- species, the nucleophile or the base. So we can either treat it as a nucleophile or we could treat it as a base. And really we just talked about nucleophilicity versus basicity. That is, how strong is the base? How good is the nucleophile? One's the nucleophilicity is the kinetic component, and basicity is the equilibrium component. So if it's a strong base, what we tend to get is elimination. There's other things that affect that as well, like the bulkiness of the base in addition to the strength of the base. But strong base tends to give us elimination in a lot of conditions. Before we get too deep into this, I want you to understand also the other condition that favors elimination is temperature. And looking at the reactants, I have two reactants, and then there's three products in an elimination reaction. And if you remember from your Chem 1B, you know the free energy is equal to delta G, and that's delta H minus T delta S. Delta S is the entropy term, and for elimination reactions that tends to be positive because of the formation of three products from two reactants. That means it's temperature dependent, and as temperature goes up, then what happens is the free energy becomes more negative. So delta S is positive, temperature goes up, this whole term becomes more negative. As a result, high temperature favors elimination. So low temperature is substitution, high temperature tends to be elimination. The other thing to point out is that when you do an elimination reaction, the hydrogen is removed from the carbon adjacent to the leaving group. This is often called a beta elimination. Beta being alpha, beta, gamma. So alphabetically in the Greek letters, alpha, beta, gamma, that's the order. So the hydrogen comes off the beta carbon, so that's a beta hydrogen that comes off. So it's often called a beta elimination. And when that happens, you form a new double bond. Like SN2 reactions, E2 reactions occur as a bimolecular reaction. And what we find from the rate law is that the rate of the reaction is dependent on both the concentration of the base and the concentration, that's the base, and the concentration of the substrate. The way they envision the mechanism taking place then is in the rate determining step, the OH attacks one of the beta hydrogens. Now you'll notice in this compound there's three different sets of beta hydrogens. There's these, and these, and they're all chemically equivalent, so you can only end up with one structure. if you remove this hydrogen, the double bond's here, but in essence, that's the same molecule. It just turned in a different orientation. So this is how the mechanism works. You have your base. It attacks the beta hydrogen, and the leaving group leaves. And this is a concerted process that all three happen at the same time. And this is where the double bond forms. And that double bond is formed from that pair of electrons. Now, it turns out there's some special orbital considerations that we'll have to look at later. But for these kinds of alkane molecules, where there's no particular stereochemistry in the product, we don't have to worry about it. So we talk about beta elimination. It happens at tertiary alkyl halides because what happens is when this base comes in and tries to attack the carbon center, it's too sterically hindered, and as a result, it's quicker for you to grab one of the hydrogens in the adjacent methyl groups to form an elimination product than a substitution product. There's another name for this kind of reaction. It's known as a dehydrohalogenation reaction. Because in the end, what you're getting is you're getting the elimination of the hydrogen and the halogen. And that's what makes the dehydrohalogenation reaction. This reaction is also regioselective, and you can see this in this next slide. You'll notice in this particular case there's two different beta carbons, and so when you attack the beta carbon to the left of the leaving group, you're going to end up with 1-butene. If you attack so that's this one, so we'll call this A, call that B. If you're attacking at A, you get 1-butene. If you're attacking at B, you get 2-butene. Now, if you remember, 2-butene is the more stable alkene because it has the most alkyl substituents attached to the double bond. So, like for example, drawing 2-butene, I could draw it like this. That's the trans 2-butene, and 1-butene is this. Here, you only have one substituent, and here you have two substituents on the double bond. The result is this is the more stable double bond. And generally speaking, when you have a sterically unhindered base, that equals the more stable alkene. Okay, so what's the reason for that? The reason for that is in the E2 reaction, this is a one-step reaction, and you can imagine that when this reaction takes place, because the product is lower in energy, the transition state energy is also lower. If that sounds familiar, that's because that's from Hammond's postulate, which we covered earlier in the semester. That is, the transition state resembles the product or reactant that it's closest in energy to. And if you remember, when you do hydrogenation reactions, alkenes give off energy, so when you form alkenes, they must be higher in energy than the reactants. And so the transition state is going to look like the product. The transition states then, for this particular reaction, show the base coming in at the top, attacking the beta hydrogen for the more stable product in this case, because that makes the more substitution double bond. And the transition state is putting electron density in that region there, and as a result, what you end up with is a transition state that's lower than energy than if you were to do the same reaction on 1-butene. So kind of what does this look like in practice, right? Because that's the kind of stuff you need to know. Here's a couple of examples of E2 elimination with methoxide. Again, methoxide is not a bulky base. We'll talk about that again. It's not a sterically hindered base. When it comes in, you get a mixture of two products, 70% of which is the more substituted product and 30% is the less substituted product. When you do 2-chloropentane, there are 3 beta hydrogens here and 2 beta hydrogens here, and when you do the substitution you get approximately 70%, 67% of the more substituted product and 33% of the less substituted product. So in general there's going to be a mixture of products, but the majority of the product, the major product, will be the more substituted alkene. That this happens is generally known as Zaitsev's rule. Zaitsev. And what Zaitsev said was that in dehydrohalogenation, I left a whole bunch of stuff out there, hang on. That when you have dehydrohalogenation, you get more substituted alkenes. Go back. So you get more substituted alkenes. Now there are some things that you have to consider when you do Zaitsev's rule, and the primary thing is conjugation. So if you have, for example, in this particular molecule, you notice the beta hydrogens to the leaving group. So here's my leaving group. There's a beta hydrogen here, and there's also beta hydrogens here. If you form, if you attack, let's call this A, and we'll call that B. This is the product from beta B. And you'll notice it's the more substituted alkene. The problem is it's actually more stable rather than being more substituted, that is to be conjugated. So the conjugated diene turns out to be the major product. Another way to get conjugation is to notice that I have beta A and beta B here. If I do the beta elimination between these two or these two, it leads to two different products. One product is this one, and the other product is that. And which one's more stable? Well, this one's the more stable, the major product, simply because this double bond is now conjugated with the benzene ring. So Zaitsev rule leads to more substituted alkenes, but actually what's more important is that if there's conjugation, generally speaking, the more stable alkene is the one that you get. Okay? So more substituted might not be the more stable alkene, so you have to look for the more stable alkene, and that's what is the overriding factor in Zaitsev's rule. There is another attribute of elimination reactions that you need to consider, and that is how big is this base, called the bulkiness of the base. So think about, there's a beta elimination. I have a hydrogen here, and I have a hydrogen here. And this is a big bulky base. This is T-butoxide. And T-butoxide wants to come in and grab one of these two hydrogen, either hydrogen A or hydrogen B. Well, which one can it grab the easiest? Well, because this is a bulky base, the oxygen, just like it's not a very good nucleophile, it's a base that can't reach in and grab internal hydrogen. So when it comes in to grab A, it has a harder time than when it grabs B, and as a result, you tend to get the less substituted alkene when you're dealing with a bulky base. With a less sterically hindered base, it would be the opposite. So methoxide ion would tend to give you the more substituted alkene, but bulky bases tend to give you what are known as anti-Zaitsev eliminations. So if you want to think about like how this breaks down, and chemists are really good at making different kinds of reagents. If you look at ethanol as the base, what you end up with is primarily the more stable alkene. T-butoxide, it switches, it becomes 73% the less stable, and then this guy, which is even bulkier because of the addition of an extra carbon really right here, you end up with 81%, and then this guy, which is bulkier than all of them, tends to give you a higher yield of the unstable alkene. So it turns out there's another way that you can end up with the less stable alkene, and that's if you have a bad leaving group. So here is my bad leaving group. Fluorine, remember we talked about leaving groups, so alkyl fluorides tend not to be used in substitution reactions because they have a tendency not to be able to leave. And when that's the case, what you end up with is you end up with 1-pentene for 2-fluoropentane as the major product, as opposed to 2-pentene, which is the more stable product. So far, just kind of quickly to summarize, and I'll talk about why that is in the mechanism, but quickly summarize. Zaitsev, that's more stable alkene. Problems with Zaitsev rule, conjugation equals the more stable alkene. So, Zaitsev's rule is really just about degrees of substitution. So you don't always get the most substituted alkene, but you always try to get the more stable alkene. So you don't always get the more substituted, but you try to get the more stable. And if conjugation is involved, that's one of the factors that gives you Zaitsev essentially eliminations. But the other ways you can do it is you can have a bulky base or bad leaving group. Okay, so what does the bad leaving group have to do with anti-Zaitsev? So if you look at the transition state for the 2 beta, so remember this is, we'll call it beta A, and we'll call this beta B. When you have a bad leaving group, you essentially have to push the fluoride off of the structure. And so when the base comes in here and tries to push the electrons back into a pi bond that forms here, okay, that's where the pi bond wants to form, it's going to push negative charge onto this carbon, a lot of it before this fluorine leaves and behaves like a good leaving group. It actually just takes off. Okay, so the result is negative charge on the carbon with the beta hydrogen. And if you remember a discussion from carbocations that are more substituted are more stable, and then we talked about carbanions. And for carbanions, the less substituted carbanion tends to be the more stable one. So with a bad leaving group, you have a carbanion-like transition state, which leads to a less substituted alkene. Groups. One is just the tendency for stability of carbocations. That is, carbocations tend to be more stable when they're more substituted. So this is the least stable carbocation, that's the most stable. And that carbanions follow the opposite trend. That is, more substituted carbanions are less stable, and least substituted carbanions are most stable. Experimentally, you can see it in the use of different halides as the leaving group. So for 2-halohexane, that's what this would be called generically, 2-halohexanes. What we find is that you get a mixture, always get a mixture of E and Z products, but as you go to more, I guess starting from the bottom, from poorer to better leaving groups, right, you get more of the more stable product and less of the unstable product. So you notice fluorine, let me erase that there, fluorine is the worst leaving group, and it gives you the most unstable product. Iodide is the best leaving group, and it gives you more of the stable product. You know, another important aspect of these reactions is the relative rates of reactions at different alkyl halides. So if I have for example, a tertiary alkyl halide, that's this, all right? The rate of the reaction is fastest. And it's the fastest because the product is the most stable. And going back to the slide where I mentioned Hammond's postulate, it's the most stable because there's the most substituents on it. For primary alkyl halides, those are the slowest of the elimination reactions. Okay, so to summarize, let's make a summary slide. E2 reactions. Okay, we'll go kind of in reverse order, perhaps because it makes more sense to me that way. Fastest is tertiary alkyl halides. For elimination reactions, it's bimolecular for E2. This is favored by strong bases and high temperature. The other aspect of this reaction that's important is that it tends to form with unhindered bases tends to form the Zaitsev product. Oops, let me go back. I accidentally scrolled forward. Tends to form the Zaitsev product. But there are lots of ways to get anti-Zaitsev. Anti-Zaitsev would include to get if you want to talk about how you form anti-Zaitsev. So we get anti-products. You can have a bulky base, and you can have a bad leaving group. The other thing that can give you anti-Zaitsev products, really not the most stable alkenes, is or not the most substituted alkenes, is you can have conjugation. People don't tend to think of that as anti-Zaitsev because it's not truly the most unstable alkene that you're making. But Zaitsev's rule is most substituted alkene. Conjugation can give you products that are not the most substituted, but they are the most stable. So in that essence, they follow the spirit of Zaitsev's rule. So the other mechanism that's important to understand for elimination reactions is the E1 mechanism. And the E1 mechanism involves the formation of carbocations, so just like an SN1 reaction. E1 reaction, the rate determining step is the formation of a carbocation. That is, in this particular instance, it would be that the leaving group leaves. So here, that guy is just going to take off. And in the formation of the carbocation, the second step, and the subsequently faster steps would involve the elimination of the beta hydrogen. Okay, so if you think about energetics and energy diagrams again, SN2 and E2 essentially follow a similar kind of mechanism, that are similar kind of reaction energy profile, except in E2 reactions the product is higher in energy, but it's a single step mechanism. In an E1, you're going to have a reactant form a carbocation, another transition state, and the formation of the product. Okay, so that's the kind of the idea. Okay, so but because it's a two-step mechanism, this first step requires only the substrate, my alkyl halide. It's not dependent on the quality of the base as much. So, slow step, formation of carbocation. This is what I was talking about, this step here. Fast step, subsequent elimination of a beta hydrogen, and it tends to follow Zaitsev's rule. That is, it tends to give us the more stable product. Now, here's the thing. When you have a carbocation, and we're showing this elimination here, the other thing that's possible is that you get rearrangement. So just like in SN1 reactions, E1 reactions tend to be plagued by rearrangements. Okay. One of the kind of a good question, like, what kind of base do you use to do E1 and what kind of base do you use to do E2? And in principle, just like SN1 tends to be less favored in terms of like usefulness than SN2, E1 is less favored in terms of usefulness than E2 because you get this carbocation formation. But the way you do a SN1 reaction or an E1 reaction is you use a poor base. And a poor base in this case is also a poor nucleophile. So then people often ask the question, well, how can this water, which is a bad or a weak base, how can it remove a hydrogen from an alkyl group? Because, alkyl groups have very high pKa's, they're not very acidic, and water is a really weak base, so it doesn't make any sense. The answer actually is in this carbocation. And it turns out the carbocation has the ability through hyperconjugation, to stabilize the electrons in the carbon-hydrogen bond, and that electron withdrawing property of this carbocation causes this hydrogen to be a lot more acidic. So you got a positive charge, reduces the pKa, remember that makes it more acidic, and then that allows a weak base / nucleophile to remove the proton. If you're asking the question now, there's a subsequent question that might be popping up in your head. How do you control between substitution and elimination? The answer, and we'll get to this at some point, is temperature. Okay. So, like an E2 reaction, you get Zaitsev elimination, more stable alkenes are formed. So if there's conjugation, just like in E1 reactions, you're going to get more, or E2 reactions, you're going to get a more stable alkene sometimes rather than the more substituted alkene. Transition state that leads to the more stable alkene is the more stable one. So Hammond's postulate again, because the intermediate, when we're talking about the formation of the product in the second step, it's faster to form the more stable product than the less stable product. Okay? We talked about in our survey of leaving groups in SN1 and SN2 reactions, we talked about qualities of the leaving group, and just like in substitution reactions, the most reactive is the alkyl iodide and the least reactive is the alkyl fluoride. But unlike substitution reactions, alkyl fluorides are reactive in elimination reactions because you can use a stronger base than fluoride to push it off, but it tends to give us anti-Zaitsev products. So, just a quick summary. Primary and secondary alkyl halides will typically undergo E2 reactions. Tertiary alkyl halides principally go by E1 reaction, but if it's a strong bases, like very strong bases, almost always favor E2 because the strength of the base causes the rate of the E2 reaction to be high enough and the concentration is high enough that it forces the reaction to follow primarily the E2 mechanism. Okay, so tertiary alkyl halides can go by both E2 and E1. So, one of the things that's confusing to students is that, SN2 at a tertiary alkyl halide doesn't exist. So why does an E2 reaction occur at a tertiary alkyl halide? The answer is actually pretty simple if you draw the molecule. So here's a tertiary alkyl halide. In order to get this group to leave in a substitution reaction, the nucleophile has to come in here. But to get it to leave in an elimination reaction, it only has to hit to here. So it doesn't have the steric hindrance problems that substitution has. So E2 reactions are faster at tertiary, unlike SN2 reactions. And their E2 are faster because the transition state stability to form the more stable or more substituted alkene is better or lower in energy. If you want to favor E2 reaction, which is typically what people will want to do, then you're going to have a strong base and a high concentration of strong base. And if you're going to favor an E1 reaction, then you have to have a weak base. And the weak base makes, again, if you're looking at the rate law, makes this number low, makes the rate constant low. And if you have a low concentration of base, that makes this first term even lower. And as a result, this is the dominant consideration, K1 and the alkyl halide concentration. So what I'd like to kind of talk about next is what we know as the stereochemistry, stereoselectivity of elimination reactions. Predominantly, we're talking about E2 reactions, but this can be true at E1 reactions. I'll talk about it a little bit, but E1 tends to always give you the more stable elimination product. So we'll talk about that. So I like to break it down kind of like this. Beta hydrogen, beta carbon, I should say, with more than one hydrogen, and then you have the beta carbon with one hydrogen, and then rings, because rings are their own special consideration. So if you have a beta carbon with more than one hydrogen, product tends to be trans. That is, the bulkier groups tend to be opposite sides of each other. So trans bulky groups. When you have a beta hydrogen, just a single beta hydrogen, what you tend to get is the anti-elimination product. And I'll talk about that in a second. And on rings, you tend to get anti-elimination only as well. So let me describe anti-elimination to you. And you have to kind of bear with me when I do this drawing, because I'm not going to draw everything. What I'm going to do is I'm going to draw the two carbons that are bonded. I'm going to draw the hydrogen, which is plucked off, and the leaving group. Let's say it's an alkyl halide. So let's use bromine. Okay. They have to be in this relative configuration to each other. That is, the hydrogen has to be above and anti to the leaving group. If you were to do a Newman projection and the bromine was here, regardless of what the other groups are, right? But you can imagine if the bromine's there, you have the other ones there. The hydrogen, the beta hydrogen that gets eliminated is that one there. Because remember, this is the front carbon here. The back carbon's, in the back. So this is the beta hydrogen. The beta hydrogen that can be anti to the bromine is the one that leaves. Now, if you think about rings, the only way that you get this to show up in a ring is if you were to draw the Newman projection, and Newman projections help a lot in understanding this kind of thing, of like cyclohexane. You would have something like this, for example, and then these rest of these go like that, and that. Which of those, and this is a CH2 in the middle, and this is a CH2 in the middle. So remember, if you draw like that, there's an axial hydrogen here and an axial hydrogen here. This axial hydrogen is actually this one that's right back here. I'm sorry. It's actually this one here. Or this one here. Let me erase that and redo it. It's like this. If I draw a chair, so I'm going to put it up like this on the, like this, and this. If you're looking at these two carbons that are here, they're the carbons on this structure that are right here. The only way that you can get anti is from the axial positions. And these are not anti because they're not directly anti to each other. So this is known as an anti-elimination. Okay. So another way to do it is a sawhorse. And in a sawhorse elimination, it has to be anti, or a sawhorse diagram has to be anti, and syn elimination was when they're on the same side. And syn elimination tends not to occur. So back to my diagram that I was using earlier. Let's go back to here. When you have the formation of a pi bond, you have orbitals that line up like this. There's good orbital overlap here. This is the anti-bonding, or a component of the anti-bonding orbital. When the base comes in and attacks here, these electrons need to transfer somewhere. Remember, when bonds form when orbitals align and electrons are transferred from one orbital to another. And so for that to take place on a pi bond, or to form a pi bond, it has to be the p orbitals that are going to form, the overlapping p orbitals that are going to form in order to make the pi bond. And in order for pi bond orbitals to interact in such a way that you form the double bond, is they have to be parallel to each other. They have to be lined up with each other. So in order for this bond to form effectively, these orbitals have to be lined up with each other. Okay, so anti-elimination, though, is only important if it's E2 and if it's only has one beta hydrogen that it can eliminate. And that's what dictates what the structure is going to be when the product forms. So again, it's an anti, requires it to be in a staggered configuration. It's a backside attack to get the best orbital overlap. This is orbital overlap. In anti also, the other thing that anti-elimination avoids is, remember, the base has got a negative charge and the leaving group has a negative charge, so they won't interact with each other. Okay, so in part of the stereoselectivity, though, is if you had the elimination of this, and that's your beta hydrogen, you could form two products. The product that you form is the one where the larger groups are away from each other instead of next to each other like this. And it's an answer of why that happens is just because it's the more stable alkene. And it turns out anti-elimination isn't a problem when you have, again, here you have two hydrogens, when you have two hydrogens over here. So thinking about the elimination, right, the elimination can occur with the bulky groups opposite of each other, and these are the eliminating groups, or they can happen with the bulky groups next to each other. And again, that also produces anti-elimination. But remember, the key characteristic is that on the beta carbon, there are 2 beta hydrogens. So you have the choice of producing anti-elimination with the groups apart from each other. That's this option here, or you have the anti-elimination with the groups on the same sides as each other. And since this is the less stable alkene and this is the more stable alkene, that transition state energy is going to be lower. Okay, so the 2-pentene with the E configuration or trans configuration will be the more stable one, have the lower transition state energy, and be the major product. So let's go through the exercise of trying to figure out what the major product is going to be for this reaction. Okay, so here's my leaving group. I don't have a beta hydrogen on this side because the beta hydrogen would have to be attached to that carbon. So since I don't have a beta hydrogen here, I know that I'll have to have one of these hydrogens removed. Now there's 2 of them there, so I don't have to worry so much about anti-elimination. So I'll get a mixture of the major and the minor product, and in order to draw the structures of the product, you have to recognize it's a 1, 2, 3, 4, 5 carbon chain. So you can draw it like this: 1, 2, 3, 4, 5 carbon chain. On carbon number 4, you're going to have 2 methyl groups. On carbon number 5, you're going to have a methyl group. Or sorry, 3, you're going to have a methyl group. And between carbons 2 and 3, you'll have a double bond like that. So those are your 2 possible products. That's actually the major product. And then the minor product will look something like this. And again, this is your CH3. And all I did is, once I've drawn the major product, and remember, I just drew zigzag like you normally do when you do a line structure, I can figure out what the minor product is just simply by switching the tail of it to be towards the larger groups. This is my minor product. All right. So let's look at what happens when you only have a single beta hydrogen. So here in this slide, what it shows is the elimination of this compound. I have a phenyl group. Phenyl group is a benzene ring, so that's actually that. Okay. And there's only, and here's my leaving group, and on this carbon, on my beta carbon, there's a single hydrogen. And the preferred, and this, you don't worry about this guy. That's not on the beta carbon. That's an alpha hydrogen. So we're not eliminating alpha. We're eliminating beta. So when we're looking at this elimination, this configuration that's shown here with a hydrogen opposite the bromine is what you have to have for the elimination to take place. So when the elimination takes place like this, the 2 CH3 groups, the 2 that are in the back, will be together. So that's why those 2 groups are, in relative configuration terms, they're Z to each other. They're on the same side. On the other hand, if the configuration of this carbon or this carbon had been different, so you know this is 2s, 3s, and what they did, they made this 2s, 3r. So what they in essence did is they switched the position of the CH3 and the C6H5, the phenyl group. In order to get an anti-configuration, this group is in the back and this group is in the back, and as a result, when beta elimination occurs, that is this mechanism here, okay, when beta elimination occurs, this group, the phenyl group, is on the same side as the CH3 rather than like it is here. Okay, so how do you do these problems? If you're good with hatch and wedge, you draw the hatch and wedge and you can rotate these groups around each other in order to get the hydrogens and the leaving group, that is this leaving group and this hydrogen, to be be anti to each other. When in essence that means opposite sides. So anti could also be like this. These two groups are also anti. So if you can get them in that configuration. I like the particular configuration your book shows here because in that configuration you can see the relative orientations of the groups once the elimination takes place. So what happens in an E1 reaction that's different than an E2 reaction, that causes E1 reactions not to care whether or not you get anti-elimination? So think about what's going on in this particular reaction that's shown here. This is an E1 mechanism. E1 is promoted, just to review a little bit, E1 is promoted by the use of a protic solvent. The protic solvent stabilizes carbocations, so it tends to form carbocations more quickly. And it's also a weak base, so again that disfavors or slows down the E2 reaction. So we have an E1 reaction mechanism, poor nucleophile / base, protic solvent to promote carbocation formation. So look here at those guys there. Those are the particularly important ones. So let me just draw it like this. So this has got my Cl on it, okay, and let's just say it has a stereochemistry to it, that the Cl is pointing forward, and then in the back I have a hydrogen like this, and then I have on the other side I have, let's say I have a stereochemistry to this hydrogen, so there's my hydrogen that's like that, and then on top of that I have a CH3, okay. So I want this, and this is a CH2CH3. I'm just going to call that R, and this is a CH2CH3, so I'm just going to call that R as well. So those are this is my R group here. How does elimination take place on here? So if it's an E1 mechanism, then what happens is this group leaves, and in the E1 mechanism and the formation of the carbocation, you still have your stereochemistry of this group here. But what happens to the stereochemistry at this carbon? It becomes trigonal planar, like this. So think about the orbital that is here. It's a p orbital that's up and down. I kind of drew it a little funny so it doesn't quite look up and down. But it's up and down perpendicular to the plane of the molecule at that point. So R, this group, and this group, those are all in the same plane together. This bond can rotate, and it can line up in the configurations that's shown, or it can line up when it's rotated 180 degrees. So the 180 degree, for example, will be like this. So because it can rotate, and again, remember, anti-elimination takes place because you get good orbital alignment. When the molecule forms a carbocation, that part of the molecule is planar, and the p orbital can line up with the R group in one position, that's like as shown here, or the R group in another position. And as a result, you tend to get the most stable carbocation related product. That gives you the most stable transition state to give you the final product, which is going to be the elimination product of the largest groups opposite of each other. So let's summarize very quickly what we know about stereochemistry in these reactions. So for SN2 reactions, you get inversion. So inversion, you only get inversion. And you get it if you have a stereocenter chiral carbon, you get an inversion of that center, a relative change in the configuration. On the other hand, for SN1, you get both R and S. So if you have an R reacting, you get an S. You can get an R and S product. If you have an S reacting, you get R and S product. But the relative configuration is generally mixed up. So you have a mixture of enantiomers or distereomers in some cases if you already have another chiral center, and you get slightly more inverted product because of that intimate ion pair that forms, and it blocks the attack of the nucleophile. For E2 reactions, again, SN2 and E2 are concerted reactions. You tend to get both E and Z isomers where the largest groups tend to be opposite of each other. The only time that doesn't happen is if the beta carbon, where you're taking the hydrogen from, there's only one, and that tends to limit you to one stereoisomer that's formed. And again, the stereoisomer that forms depends on the configuration of the reactant, just like it does for an SN2 reaction. So for an E1 reaction, again, you have both E and Z isomers. You get a mixture, but you tend to get the mixture where you have more product where the largest groups are opposite sides of the double bond. So let's talk about what could happen in a ring, a six-membered ring, like a cyclohexane ring. And imagine what's given in these positions are actually methyl groups for now. Just think about that as a CH3. Okay, and so all of these are all CH3s like this. If the leaving group and the hydrogen are axially oriented to each other, that means they're set up to go in the anti-elimination already. There's a lot of things that could influence this. Let's say I had CH3 over here and a CH3 over here. So what would happen in that case? Well, if there's only the one hydrogen, then the elimination has to take place along this side and has to be in such a way that the hydrogen and the leaving group are axial to each other. On the other hand, if I had a hydrogens on both sides of this ring, so let me erase this real quick and start over. Let's say I have a CH3 here. Or actually do this. Let's do a hydrogen here. And let's make this into a CH3. And then I put a hydrogen here and a CH3 here. Then rather than the elimination taking place on this side, it would prefer to take place on this side if this was the only orientation that you could get for the leaving group being axial. Because remember, if I do a ring flip, this is going to go, this X group, the leaving group, is going to go from the axial position to the equatorial position, in which case it won't eliminate. So you can have a situation where you have one beta hydrogen on each side, and the molecule can only eliminate on the beta hydrogen that's axial to the leaving group. Sort of to re-emphasize some of this, you have equilibrium between the positions of the leaving group, between its axial and equatorial position. And in fact, if this is the only thing that you have, the Cl if Cl is the only substituent you have on the benzene ring or the cyclohexane ring, it tends to be in the equatorial position. If, for example, I added a methyl group on this side, then what would happen is, or a larger group, when this ring flips, the CH3 prefers to be here, and what you do by doing that is you alter the equilibrium so it favors more this way than it does that way. So sort of the way that they're showing right now is that this arrow is larger because it favors the Cl being in the equatorial position. But if you had a group in an axial position that's larger than the chlorine, that group prefers to be in the equatorial position, and that'll force the axial positioning of the chlorine, the leaving group, in the molecule. So what effect does that actually have? Well, if you're looking at rates of reactions, remember, you have to have, when we talk about collision theory and rate laws, you know that the rate constant is proportional to a couple of different things. One is collision frequency. The other one is the the fraction of collisions that occur in the correct orientation, and the other one is energy. So because you force, if you add a large group in this position here and it forces the molecule to go push that to the equatorial position, there will be more collisions, that is this term here, of the base to the beta hydrogen that are in the correct orientation to produce the product. So regardless of what the energy or the temperature of the system is and the frequencies of collision is, by altering the structure of the substituents on the ring, by, for example, putting a methyl group that forces the chlorine to be axial, you can change the rate of reaction when this reaction takes place. If the mechanism is E1, again, using methanol as an example, and if you remember, the previous example was ethanol. But if you use methanol, that's again a poor base, a weak base. What happens is, even though this chlorine's not in the axial position, what happens is when it leaves, because it's an E1 mechanism, it forms a carbocation. That p orbital is aligned with this hydrogen because this becomes trigonal planar. And as a result, it doesn't have to be in the axial position if it's an E1 elimination. Now, if you use a strong base, that favors the E2 elimination. Weak base favors E1. So you can in an E2 reaction, that is going to be strongly affected by substituents and their orientation on the ring. So what I think I'm going to do is stop at this point here, and I'm going to save the discussion of the competition between elimination and substitution for another lecture. So we have one more lecture on this topic, and then we'll move on to the next subject material. Again, if you have any questions, feel free to contact me by email or text message, and I hope you have a good break.